backtracking as a systematic way to explore in a depth-first manner the entire search space, right? And then we talked about your way to prune away parts of the search space. And this technique is called branch and bound. And the idea here is that you are trying to derive some sort of a lower bound for the minimum cost solution that can be found inside some part of the search tree. And if that minimum cost solution happens to have a higher cost than a solution that you already found, then there's no need to look further. Okay, so that's the basic idea. And we talked about how you can use this to solve traveling salesman problem somewhat faster, and we actually mentioned that if you follow, if you do this, then there are actually of the order of 5,000 possible positions to consider in the search tree if you expand it fully. And once you use this kind of a technique, then you end up okay, so you end up at maybe exploring like 30 nodes or 40 nodes instead of exploring 5,000 nodes. Okay, and we said that if you combine it with another heuristic, which basically first looks at paths that give you the lowest bound, then what you'll do is you'll in fact be able to follow this path and be able to get to the solution first, right, without really exploring any part of the search space that really doesn't have solutions. Okay? So by combining heuristics with the bound, you can improve the solution. You can often obtain even better solutions. Okay? In practice, for some problems, it may not be easy to come up with these sorts of lower bounds in advance, right? So we said, okay, for traveling salesman, by thinking about a problem in a certain way, you can come up with hard lower bounds that you know for sure. Every solution is better than is going to be more expensive than that lower bound. Okay, but there are some problems where it's either too difficult to come up with lower bounds, or it takes too long to come up with compute a lower bound. So in those cases, what you might do is you might end up using an estimate of what is the minimum cost that can be achieved there, right? So it's no longer a proof, but you have some level of confidence that it is the lowest amount of cost. So that is, strictly speaking, not a branch and bound technique, but it is a way of applying the same idea with approximation of, with some estimates of lower bounds rather than real lower bounds. And then you can go even, you can relax this even further by saying, okay, I'm not even trying to find bounds. What I'm trying to find is, I'm just using some sort of heuristics to say whether I'm likely to find good solutions within a subtree or not. Okay, so many problems that involve, playing games, okay, they just do this. So, for instance, if you take a program that plays chess, all that it is doing is it's developing a search tree like this. But obviously, exploring this search tree to any significant level of depth is going to be very expensive, right? So even if you unroll it to two possible moves, there's an enormous number of possible configurations of the chessboard after two moves, and systematically exploring that is going to become hard. So what happens is that in these sorts of games, you have some heuristics to assess the quality or you associate some sort of a merit with each configuration. So if you say, okay, here is this position with certain pieces in certain places, and then you have some function that assigns some sort of probability of winning with that configuration. Okay, and this, of course, this could be a lot of guesswork involved, but still it's the best you can do for certain problems, and then you just proceed and try to come up with some solution. Okay? And of course, in some cases where even though you seem to be using some heuristics, you might get a good solution, as we talked about the Knight's Tour problem, right? So Knight's Tour is also another backtracking-based search problem where you are trying to figure out how to navigate through the squares in a chessboard using a knight in such a way that all squares are eventually touched and they're touched exactly once, right? So the way you do this is by, again, doing some sort of forming a search tree and using backtracking, but again by using this heuristic that favors visiting squares which have fewest non-visited neighbors, right? So you go to a square if it has a very small number of unvisited neighbors, right? Why? Because you want to say, okay, if my ability to come back to that square is proportional to the number of unvisited neighbors, because I have to come to that square from one of its unvisited neighbors. So if some square has only, say, 2 unvisited neighbors, then maybe I better visit it now, because maybe in future I won't have an opportunity to visit it, right? So that's the kind of heuristic you might use, and that heuristic might allow you to come up with good solutions. So this is sort of the general approach for dealing with these sorts of search problems where the search space is exponential and you're simply trying to manage the search space, explore it systematically and as efficiently as possible, trying to come up with 2 to the power n by 2 algorithms instead of 2 to the power n algorithms, right? So trying to improve the algorithm in various ways, trying to use bounds or heuristics to cut down and not explore some parts of the search space. So this is what you try to do when you are trying to find the optimal solution, and try to do it as fast as you can. The other alternative you have is to say, okay, I'm not looking for optimal solution, I'm looking for an approximate solution. Okay? So there's one thing that you really need to understand what approximate means. Okay? Approximate has, approximate doesn't mean, I'm just going to go use heuristics and I don't know what I get in the end. Okay? So approximate here has a very specific meaning, and it says that the cost of the solution is within some factor or within some difference from the optimal solution. Okay, so at the end, for instance, if you do a traveling salesman problem and you are told that you have a factor of 2 approximate solution, what that means is that the solution that you compute is guaranteed to be within a factor of 2 cost from the optimal. Okay, so you do have the key point, remember, about approximation algorithms is that you do have guarantees on how far you are from the optimal solution. Okay? And the question is whether by relaxing this optimality requirement and by saying, I don't want the absolute best, I want something that is within, say, some factor, if doing that relaxation of the problem, will that make the problem tractable? And that's what we're going to discuss for the rest of today's lecture. Okay, again, the most important thing to keep in mind is just not random heuristics that you're using. Okay, so of course we need to say what is the notion of distance from the optimal, and there are 2 basic ways. One is called additive. That means you're saying that the optimal solution, the solution that you compute, right, or the approximate solution that you compute, is within a certain difference from optimal. Okay, so once again, we're going to use this notation SA to refer to the cost of the approximate solution, and SO to refer to the cost of the optimal solution. Okay, and what we are saying here is SA equals SA plus. I'm sorry. We are saying that SA equals SO plus some constant. Okay, that's additive. Okay, factor means, we are saying SO equals, or rather SA equals SO times some factor. Okay, so very often we don't find too many approximate algorithms where the approximation is based on some, adding some constant. Okay, it's rare to find such solutions, but we do find factors often enough. Okay, and what we are going to do today is to just get a little bit of an idea of what kinds of approximate algorithms are there. We're obviously, in the next 1 hour we are not going to get too deep into the topic, but at least you should have some idea of what approximate algorithms are and what are some examples. Okay, so as I said, the approximate algorithms that differ by a factor are much more common. And so in that case, what you're saying is the cost of the approximate solution, SA, is less than or equal to some factor times SO in general, right? And if you say that the factor is constant, well then you say SA is less than or equal to K times S0. And there are certain problems, certain NP-complete problems, for which we have we are able to achieve these approximation factors, and one of them is vertex cover, right? Remember, what's a vertex cover? You want to choose a subset of vertices in the graph such that every edge is covered by one of these vertices, right? So for each edge, you have two vertices you could choose for covering that vertex, but in a vertex cover, you just need to, need to include one of them. Facility location is another problem which we'll talk about later on. So logarithmic factor means, well, it's no longer a constant. It is related to the size of the problem n, but it's not linear, it's logarithmic. Okay, so the approximate solution is more expensive than the optimal solution by a factor which is of the order of log power kn, okay, for that k is a constant. Similarly, polynomial means, well, your factor becomes n to the power k. Okay? And so obviously, if you look at the constant, logarithmic, and polynomial, for many problems, you are really interested in constant factors, and then that's something that you can easily accept. Even logarithmic factors are typically not very appealing. Okay, again, remember, we're not talking about, computation time becoming logarithmically more expensive, right? That we would easily accept. But if you are told that, you have a solution to TSP problem, which is, log square n times more expensive than the optimal, well, that doesn't look very good, right? So what you're saying here is, okay, instead of finding a solution where the cost is 1,000, you might find a solution whose cost is of the order of 100,000, or something like 100,000, right? So that doesn't sound very appealing, right? So if I said, okay, instead of 1,000, I'll find something which is within a cost of 2,000, well, that seems, like something that you could potentially live with, right? So again, these factors, once they get to polynomial factors, you are no longer in very good. The solution may not be acceptable. So let's talk about two other schemes, polynomial time approximation schemes. Okay. So polynomial time approximation schemes means you have a solution which is based on a factor. The factor is something that you could control. Okay, so that's why we call it 1 plus epsilon. Usually epsilon suggests to you that it's relatively small, right? So basically what you're saying is that you're trying to get a solution that can go as close to the optimal as possible, right? By changing epsilon, you can go closer and closer to the optimal solution. And typically what happens is that in particular, what the kind of approximation that you want is one where as you get closer to the optimal solution, you have to pay more and more in terms of computational time. This is something that's almost intuitive, right? So to get a better solution, you have to pay more, right? Now, what could happen is that as you get closer, you could have to pay exponentially more time, right? And of course, we know that how to do that, right? Because the straightforward backtracking and search algorithm, well, there you're increasing the cost exponentially, and of course, then you're going to get the absolutely optimal solution. So in a fully polynomial time approximation scheme, what you get is that for getting closer, you only have to, in a sense, pay polynomial cost. Okay. So for instance, the factor in runtime becomes, epsilon power minus k. Again, if epsilon is small, right? Epsilon. So let's say epsilon is 0.01, which means that you have a solution within 1% of the optimal solution. Okay. And what this says is that the runtime now is going to be multiplied by a factor of epsilon power minus k, which in this example is going to be 100 power k. Right? And again, since for many of these problems, these are problems which are that have exponential complexity, which means that very often you're working with n that are not incredibly large. Okay, and as such, if you have something that whose runtime increases by this factor, it may not be too bad. Okay, so we will, of course, in theoreticians, very much like these, fully polynomial time approximation schemes. So it's not always easy to come up with these sorts of schemes, but we will again go through one example to just give you a flavor of, how you get, how you can design approximation schemes where you can get closer and closer to the optimal solution by paying only polynomial amount of by only increasing the computation costs polynomially. So there are various problems. Once again, set cover is an example of a problem where you have a logarithmic factor between the approximate algorithm and optimal algorithm. And then there are other problems like max click and graph coloring, where approximation algorithms come within a polynomial factor. Okay, and fully polynomial time approximation schemes are available for a few well-known problems like knapsack, bin packing, which is something we'll talk about, and again, bin packing is very closely related to knapsack, Euclidean TSP, so traveling salesman problem on Euclidean plane, right? Which means that we have the triangle inequality, right? So if you have if you have 3 points, let's say 3 vertices, right? U, V, W, then there is a triangle inequality which says that this distance plus this distance is going to be greater than or equal to this distance. Okay. So obviously, if you just think of general graphs, this obviously need not be satisfied, right? So this is, let's say this is C1, C2, C3, right? In general, I could say give C3 any value, right? So the cost of the edge could be anything, right? If the triangle inequality holds, then I have C1 plus C2 greater than or equal to C3, which helps, as we'll see later, that is, serves as a basis to find approximation solutions, and as such, you can solve Euclidean TSP faster than general TSP problems. Okay, so let's start by considering one simple problem, bin packing. Okay, so what's a bin packing? So you have objects of different weight, and you have a number of bins, and you want to put these objects into the bins, and each bin, of course, has a fixed capacity. You cannot go beyond its weight capacity. So you put objects into the bin, and then you can no longer put anything more. Then you go to the next bin, and so on. Right. So now there are various ways to do this, and again, most of you should be familiar with these first fit and best fit types of solutions to this problem. Okay. So by the way, bin packing is NP hard, otherwise we wouldn't be talking about it here. And again, NP hard because if you want to find the absolutely optimal solution, it is it has the same difficulties as you have with knapsack. Okay. So let's look at a first fit algorithm. All it does is you have some number of bins, right? So what you're going to do is So you are going to take the items one by one, and then you're going to put it into the first bin that can fit that item. Okay? So which means that obviously a number of bins at the beginning, most of the bins towards the end are going to be empty because you're not even going to get there, because whatever object you have is going to going to fit in one of the earlier bins because the bins are not full yet. Okay? So now the question is, how can you analyze how good the solution is? Okay? And to do that, we can make this assertion, right? So all open bins except possibly one are more than half full, right? Or in other words, what we are saying is that there can be at most one bin which is less than half full. Okay, and then the rest are all, of course, completely empty. So the notion of open bin is that there are a number of bins that are empty. Okay, we are not going to consider them. Okay, so those are considered closed at this point. We are looking at bins which have something in them. And then what we are asserting here is that at most one of them will be less than half full. And why is that? Actually, the proof is quite easy. Okay, so let's say there are two bins B and B prime that are less than half full. Well, then you can take the content of one of the bins and just empty it into the other one, right? So obviously, there should have been no reason to have two such bins, because everything that is in the second less than half full bin would have fitted in the first less than half full bin. So the first fit algorithm would never have gotten to a point where it has these two. Yeah?
So all bins have the same capacity?
Correct. All bins have the same capacity, right? So it's very easy to see that, right? And once you have this, that at most one of them is less than half full, you immediately get a factor of 2 from optimal, right? Because the best solution, what can it do? It can keep every bin absolutely full, right? And what we are saying here is that this first fit algorithm is going to keep all the bins at least half full, right? Not all but one, at least half, right? So essentially, that means it's it's more or less, technical definition of optimality says you should only have a factor and not a constant. In this case, we have a factor plus a constant, right? So we have 2 times optimal plus 1, because the last one could be less than half, right? Everything else could be, just half plus some minute extra quantity, right? So that means you cannot combine them, right? And therefore you could have 2 times the so the optimal solution could have all the bins full, whereas the approximate solution, you could have each bin only half full, right? Except the last one. So that means you'll have 2 times the number of optimal bins plus the last one, which could be almost empty. So that adds plus 1. So that's why you get SA is going to be 2 times SO plus 1 in the worst case. Any questions? Okay, so you've heard of best fit algorithm, which is another basically greedy algorithm. And instead of putting it into the first bin that's large enough to hold the item, you find the item that find the bin whose capacity is closest to the size of the item. Of course, it should be a little bit larger, right? Otherwise, you can't put it in. But you want to find the best fit, right? So out of the remaining capacities of all the open bins, which one is the closest fit to the next item? Okay, so if you look at that, then, well, unfortunately or fortunately, the best you can do in terms of proof is, you might think that best fit is somehow better than first fit, but in terms of proofs, we really cannot do much better, right? We can only show that it is within a factor of 2. Okay. So we can try slightly some improvements to these algorithms. So one improvement you can do is to first sort the items. Okay? So the idea is that you will put the largest items first. Okay? And the point is that, well, small items probably can go into, nooks and, cracks in the, right? So that's the basic idea. So you put all the big, this is how you, presumably when you pack your luggage, this is what you do, right? You want to put all the big items there, and then the small items you'll just somehow find a place, right? So that's the basic strategy here. So you're going to just sort them, put the big items in their place, and then try to find, and you can apply that to first fit or best fit, okay? And then we won't go into the proofs, but you can show a proof where the factor is pretty close to 1. Right? 11 by 9, that seems quite close to 1, and you probably would be quite happy if you can achieve a factor of 11 by 9. Then again, if you're packing your luggage, if you're packing it within a factor of 11 by 9, I'm sure most of us would be quite happy, right? So that's a pretty good approximate algorithm, and again, it's not at all complicated, right? It's a pretty simple algorithm. It's going to be efficient and gives you pretty good solution, right? So again, it's an example of how some problems which are NP-complete in general can in fact be solved in fairly easily using approximation algorithms. So let's start to get into that. It's a technical point. Okay, so that's sort of the simplest problem we will consider in approximate algorithms. So let's look at the next problem, which is set cover, right? I'm sure all of you have some intuitive idea of what set cover is. So let's define it formally, right? So you have a set B, and then a collection of subsets of B, okay? And then you want to pick some of these subsets among S1 to Sn such that the union covers the entire set B. Okay? So that is the set cover problem. Again, the idea is that the elements from Si1 to Sik that you've chosen, right? Those elements should cover all of the elements in all of the sets. Right? So again, B is essentially the union of S1 to Sn. Right? So B contains all of the elements in all of these sets. And obviously there's some kind of duplication of elements across these sets S1 through Sn, and you want to find some sort of a minimal collection of sets Si1 to Sik, right, such that they cover all of the elements. Okay, so let's talk about a greedy algorithm for this. It's again very intuitive. What you try to do is you pick a set that maximizes the number of uncovered elements. Okay, so that's the idea. So let's go through this step by step. So initially you set cover is empty and covered equals empty, right? So covered refers to the all the elements you have covered so far, right? So covered refers to this quantity, right? So you so far picked some number of sets, okay? The sets that you have picked are going to be in cover, and the union of the sets that you have picked is going to be called cover, right? Because that's an element in B that you have actually covered, right? So what you're going to do is again, cover consists of the set of the subset of sets from this collection that you've already picked to be in your set cover, right? So any new element that you're going to pick is going to be in S minus cover, right? So you pick something in that has not been picked so far, and the way you're going to pick this is so that the number of new elements that it's going to bring to the cover is maximum. Right? So the idea is, well, you want to cover B as quickly as possible, and how do you do that? By making sure that for each set you pick, it brings in enough number of new elements. Okay? So then once you pick that new set, you're going to add that new set to the partial cover that you have built up, and you're going to add all the elements in that set to the set that is covered, right? And then you're going to repeat this until the covered set equals B, right? So that's this loop. So while covered not equal to B, you continue this, right? So it's a very simple algorithm for doing set cover. So let's